Okay, I think that now it's really time to begin. So welcome to the Best of ACM competition presentation. So today we will have 7 teams who will present the solutions to the challenges they have chosen. The challenges were 4. We have got the solutions for the first, third, and the fourth challenge. And now I would just invite Monte to start with the presentation of the first challenge. Thank you.
Thank you. Good day to everyone. I'm happy that we are here. I would like just to say a little about the first challenge. So it was a challenge that was maybe most actual in the time due to the COVID situation that's happening in the world. So we wanted you to present a model that will predict the number of claims for the car insurance, especially the MTPL insurance, and therefore there was this challenge in collaboration with data that was publicly provided by Apple and Google, and of course the data that was provided by the Slovenian police. We have received 6 solutions and we have narrowed it down to 2 of them. So the teams VIVN and the Bunny's model. So without any further explanation, I would kindly ask the team VIVN to present their solutions. And I think we've discussed that every team has 10 minutes for their presentation, and then we have some additional time if there will be any questions.
Okay, thank you. And can you hear me?
Yes, we can.
Okay, so I just share my screen. So you see my screen? Okay. Yes?
Yeah.
Yes, we do.
Okay. So first, let me introduce myself. My name is Nguyen Hai Vi from team VYVN, and I am student at Department of Mathematics and Modeling at the National Institute of Applied Science of Toulouse, France. And currently, I do my internship at the National Center of Scientific Research in the domain of deep learning. And so let's move on the subject. First, we analyze a little bit about the correlation between the mobility and number of accident people. And the figure A shows the number of accident people in the first 20 weeks in the Slovenia, and the figure B shows the driving mobility provided by Apple. And both of them attain the weekly maximum on a Friday, corresponding to the vertical red lines, and the weekly minimum on the Sunday, corresponding to the vertical green lines. So the fact that both of them attain the weekly maximum and minimum on the same days of the week, so that there is a very strong correlation between the mobility and number of accident people. And this is quite important remark for the prediction part. And so let's talk about the general principle of model and how to train model. Let's say we have built a model with different parameters. And so we will input a feature in the model, and from there, the model will output a prediction for the number of the accidents for the following day. And beside that, we have also the label with the real value of the number of accidents of that day. So by comparing the prediction and the label with the real value, we try to optimize the parameters of the model in the way that the prediction is as close as possible to the real value. Okay, and so by doing that with different pair of feature and label like that, we have a model with give a prediction close to the real value to the label, and we call that training models. And so how to prepare data for training models? In fact, I just talked about the feature, and in fact, the feature is just a set of the consecutive elements in the series, and we call that a window. And the label is the day next to just next to the window. And so the idea of our model is that from the feature of the consecutive days, we want to predict from there, predict the number of accidents for the following day. And so by just sliding the window along the series, we have different couple of feature and label like that. And so we have a training data set for training models. And we take the first 200 elements of the series for training model and the rest for validating their performance. And with that idea in mind, we try with different model. And from there, we compare their performance and try to choose the best model. And then we want to make an even better model by combining the best models. And here in particular, we have Gaussian process model, random forest model, linear regression, multi-layer perception, and the simple recurrent neural network. And the last two models are the deep learning model. And let's talk about Gaussian process model. So we don't have a lot of time, so I just talk about the main principle of Gaussian process model. So let's say that we have a set of n observation, and an observation corresponds to a feature xi and the corresponding label yi that we just created, okay? And we try to fit a Gaussian process model that with the mean vector pass through on the observation, and from there we have a multi-dimensional probabilistic distribution. And so for the point that we do not observe before, using this distribution, we can predict it for the point that we do not observe before. And an important point is the choose of kernel with either covariance matrix for the distribution. And an important point is that the linear combination of a kernel is also a kernel. And normally the choice of kernel depend on our knowledge about the structure of data. But here we do not have any particular knowledge about the data. So we just try with different kernel, and finally we came up with the kernel with either linear combination with 5 basic kernel with a Martin kernel, RBF, rational quadratic, dot product, and Y kernel. And another important question is how to choose the number of elements in the window, and we call that the window size. And for that, we train the model with different window size on the training set, and then we calculate the mean absolute error on the validation set. And here we see that with the window size equal to 30, we got the minimum mean absolute error on the validation set. So we choose the window size equal to 30. And with that model, we have the predictions. So in the figure 3, and we measure the performance of model by the mean absolute error and the R-squared score. And next, the random forest model is a typical machine learning model, and basically it's an aggregated model of different decision tree. And similarly, we try with different window size, and here we see that with window size equal to 30 or 40, we have the minimum of the mean absolute error. However, for the random forest model, when the window size increase, the variance of the model will also increase. So we would privilege the small window size with E30 here. And with that, we got the prediction into figure 5. And also we measure its performance by the mean absolute error and the R-square on the validation set. And next, the linear regression model. And it's just a very simple statistical model which assumes a linear relation between a set of explanatory variables within the window and the corresponding label, okay? And although it's very simple, it is widely used because it's very simple to calculate. And similarly, we try with different window size on the training set, training the model, and then calculate the mean absolute error on the validation set. And once again, we came up with the window size equal to 30, and we got the prediction shown in the figure 7. And we measure its performance by the mean absolute error and R-squared score. And besides that, we also try with deep neural network. And here we had a multi-layer perception with 4 hidden layers. And we have tried with different number of neurons for each hidden layer. But it turns out that the result for this type of model is not really good in terms of R-squared score, but also the mean absolute error. And besides the multi-layer perception, we also try with simple recurrent neural network. And once again, it does not give a very good result. So here is the summary of the result of models. And in terms of R-squared score and mean absolute error, we can see that the first 3 models are much better than the last 2 models, although the last 2 models are much more complex. And so we would consider using the first 3 models. However, we want to make an even better model by combining the first 3 models. And the idea is that we will try the linear combination of the prediction of the 3 models. And let's say XGP is the prediction of the Gaussian process model, RF for the random forest model, and LR for linear regression. And Xi is the prediction of our combined model. It's just a linear combination of these three predictions. However, we need a supplementary hypothesis is that the linear combination need to be convex, which means that the sum of alpha 1 plus alpha 2 plus alpha 3 is equal to 1. And the reason for this choice is that assuming that the expected value of the prediction of each model is equal to the real value of that day. So by using the convex linear combination, we can easily show that the expected value of the combined model is also equal to the real value, and so the model is non-biased. And the value of alpha 1, alpha 2, and alpha 3 correspond to the distribution of component models to the combined model, and it depends on our knowledge about the importance of each model in the combined model. However, here we do not have any particular knowledge about the importance of each model. So we just choose alpha 1 equal to alpha 2 equal to alpha 3 equal to 1 over 3. So the sum equal to 1, okay? And surprisingly, we try it on the validation set, and in terms of R-squared score, but also mean absolute error, the performance of the combined model are better than each of the 3 component models. So we choose this model to predict the number of accidents. And so let's talk about how to predict the number of accidents. Let's say we have a window of 30 consecutive days that we just mentioned, and using our combined model, we have an output 1, but this is not the final result for the prediction of number of accidents, because we want to add the impact of the mobility. In the first part, we see that the mobility is very correlated with the number of accidents. And here by Apple, we had the gawking and driving mobility. And we can see that they are very similar. So we can use either one of them. And here we choose the driving mobility as the mobility factor to add to the model. But before adding it to the model, just observe the figure 11. We see that in the mobility, it has a very particular trend. Whereas in the figure 12, we do not observe any trend in the number of accidents. So we try to remove this trend from the mobility. And let's call M the mobility after removing trend. So basically, M is just the variation around the trend. So M plus 1 is the ratio compared to the standard. So the final result for the prediction of number of accidents equal to output 1 multiplied by M plus 1. And using this model, we have the prediction so in the figure 14, and compared with the report of road safety in situation 2020, we got a relative error of 60.9%. And now we have already the prediction of number of accidents, but we want also know the number of accident people. And for that, just observe the figure 15, which shows the ratio of number of accident people divided by the number of accidents in 2019. And the 3 dashed lines correspond to the first quintile, the median, and the third quintile in probability. And after calculating, we can see that the distance between the first quintile and the third quintile is very close. So which means that the ratio of number of accident people divided by number of accidents varies so little from day to day. So we can just approximate the number of accident people by just multiplying number of accidents by the median value, which here is 1.769. And finally, we want also to know the number of dead or severely injured accident people. And for that, we observe the cause of this type accident. And it turns out that there are top 3 causes for this type accident, which are unadjusted speed, wrong side direction driving, and disregarding priority rules. And we can see that this type accident comes from the lack of awareness of road user. On the other hand, in 2019, out of on traffic accident people, 2.406% are severely injured and 0.299% are dead. So assuming that the awareness of road user will not change rapidly from year to year, we can use this ratio to approximate the number of severely injured or dead accident people. So we came up with this formula. The number of severe injured accident people equal to the total number of accident people multiplied by 2.406%. And the number of dead accident people equal to number of accident people multiplied 0.299%. And using this model, we had the predicted number of dead accident people is equal to 93. And compare with the report of road safety situation, we had 30 dead accident people. And so we got a relative error of 16.25%. And knowing that we have already a reality error for total number of accident people, so the above 16%, so the reality error for that number of that accident people around 16.25% is quite reasonable as a model. And here is just the summary of our models, how the model works. Okay. And besides the model so above, we also try with more complex model, such as the deep neural network, with including 1D convolution layer, and also the layer of long short-term memory, LSTM. And in fact, the LSTM is widely used in the forecasting problem. However, in our case, it does not give a very good result. And so we didn't add it to the model. And one big advantage of our model is that it does not use the external data, but the information of time series itself. So from the time series, using our model, it can just learn automatically the structure of the data. And using the window of 30 consecutive days, it can give us a prediction for the following days. And one final point is that if we do not have data about the mobility, we do not need to add it to the model, because if we take average over a long enough period, let's say 1 week, the result should not change much, because the mobility after removing 10 is periodic and its average is near to 0. And it's on for my model. Thank you for your attention. And if you have questions, please ask me.
Thank you for your presentation. If there are any questions from the audience, I would kindly invite you to ask them.
So you can either raise your hand, or you can write your question in Q&A or in chat.
As it seems that there are no questions at the moment, I would like to thank the first team. So thank you, Kai. And I would kindly invite the second team to begin their presentation. The second team was the Bunny's model. It was a team of 2 members, so Xiaorang Wang and Chang Li. And I would kindly invite you to present your solution.
Yeah, we will make the solutions. So can I share the screen?
Yes.
Can I share my screen? Okay. Dear organizing committee, hello, thank you for inviting us to the second round. I'm Chang Li from the Bunny's model. Xiaorang Wang is my team member. Next, we will make a detailed statement on challenge 1. Our presentation will be divided into 5 parts to show our solution for this challenge. Thank you so much for listening. Next, let my team member Xiaorang Wang explain our solution.
Hello, everyone. I will explain our solution to you. In the first 3 parts, we would discuss the mobility. We divide the mobility into 3 operators: daily, monthly, and annual operator. For the daily operator, according to the scatter graph, it looks like an F distribution. So we put the F distribution function as the arithmetic operator. As the degree of freedom becomes higher, the distribution would become more and more like a normal distribution. As the value becomes more close to the mean value, the probability would increase. This will help us to avoid being influenced by the extreme value and let the results become more in general. For the mobility data, we divide them into 3 groups: residential and workplace in one group, which presents the mobility of daily schedule; retail and park in one group, which represents the recreating and the recreating mobility; and the grocery and transition in one group. This presents the working mobility. For the monthly data, according to the results of the daily operator, it looks like promotion. Many normal distributions put together. Actually, we can precisely predict the people's mobility since each of them has their own mind. So we use the promotion operator to be the monthly operator. And then it's my team member's turn.
Okay, for the annual operator, D is monthly operator result in the each group per month. 321 is the real day calculate in this year. Put theta and B into the views and make a eyeless estimation put P equals 0.01. This is just a way to get a relation between days and the monthly operator. Transition to make the annual operator. So passing the T text is enough. This is also a Brown motion process. Set this integral to make the mean value, which reflects the average level. According to the calculation, the integral of the second and the third group is 0. The integral of the first group is 9.98. It seems that we analyze the data, it is easier to see the relationship between mobility and the traffic accidents. Then we will talk about the relationship between traffic accidents and the travel mode. When we consider the relationship between travel mode and traffic accidents, we use the arch model, and participants are divided into 3 groups. The relationship is shown below. By analyzing the data and the charge given, we give the driver of personal car through not growing, but its share a death is still high in 2019 and 2020. In this graph given, a significant decline in the number of the deaths is recorded among pedestrian and traveler. During COVID-19, the number of passenger car drivers died on this road is highest. After building this three operator, we draw a relationship between the operator results and accident suffered. We use the ARC model to draw the relationship between operator result and accidents. ARC model is a white node model which has a normal distribution, and with an arrow which is a linear symbol of the past variance. After the decline of mobility can decline the injured people in the accidents. In this way, carriers with lower mobility should be encouraged to reduce the accidents.
And in the future, the traffic accidents would decrease together with the 4 types of sufferers and 3 types of hurts.
I'm sorry, we can't hear you.
Is there something wrong?
We can hear you in the last minute, maybe, or something. It seems you are muted.
Okay, hello.
We can hear you now.
In the future, okay, thank you. In the future, the traffic accidents rate would decrease together with 3 types of hurts and 4 types of sufferers. Whether using the safety belt would not be important in the accidents rates. However, the pedestrians accidents would increase, and this should be put more attention. Some safety tools should be put into use, and more teaching and more traffic rules teaching to the pedestrians should be given. In the two regions of Slovenia, the traffic accidents would increase, and this also should be put more attention. The safety prevention in these 2 areas should be added in order to improve the condition. And for the global trends, we don't have the whole data of COVID-19 and mobility, so we can't discuss it very in details. But we still can assume it would be the same as the trend in Slovenia. The whole accidents rate would decrease with some parts of the with some regions and some group of people has the increasing rate of traffic accidents, and this all should be put attention.
You seem to be muted again.
What? I'm sorry, I mute again. And the fatal rate would decrease. The traffic rate would also decrease in the future all over the world. But some group of people and some regions would have an increasing traffic safety, an increasing traffic accidents rate. This should be put more attention, and the maintenance prevention should be put more in these parts in order to improve the traffic safety in these aspects. Thank you all for listening us.
Thank you for presenting. Thank you for your presentations. Once again, I would kindly ask the audience if they have any questions to raise their hand or type them in either chat box or either questions and answers box. Anna Gordovich-Snip has a question. Please present your question.
Thank you. I actually have, now that we have listened both, I would have two questions for each of the one question would be, what would you enlighten as the, let's say, biggest advantage of what you have provided as solution? And the second thing would be whether today, given, let's say, more time, more things, eventually also the others, what you have heard, whether you would do something differently in terms of your solutions. Thank you. So for both teams, the same questions.
Okay, so I can just answer first, please. In fact, I have tried with to adding the weather data. However, when I adding the weather data in the model, it make the performance worse. And the reason for that because we just have access to the average temperature and humidity of the Slovenia, whereas the accident depend only on the local weather. So the fact that we do not have access to the local weather of a year make our performance worse. Mm-hmm. And another is that if we have more data, we can make the model with LSTM that I just mentioned, because LSTM has the capacity to memorize the past, which means that the information in the past. But here, because we have only access to the data of 2019, we don't have enough data to train the LSTM. So if we have, for example, 3 or 4 years data of accident, I think I can make a better model with the LSTM. And thank you.
Okay, thank you.
And advantage of our model is your question, right?
Yeah. I mean,
advantage of our model is that yes, do not need the external data, but just the information of the time series. And so from that, our model is just learn automatically the structure of the data, and then we can predict the number of accidents for the following days. That's one big data of our model, and it's quite simple to calculate also. And thank you.
Okay, thank you. The girls from the other team?
Yes, I'm here. For the advantages in our model, we think we draw the relationship between the mobility, the traffic accident rates, and the COVID-19. We run these relationships, and then we build the model which could show the factors influence the traffic accidents, and get the general conclusion. We use evals and R to run the data, which helps us to quantify the model. To improve the model, we think we can use the more model, the more time series model, and we can use more softwares to run our data. We can compare them one by one, and we think we can also get more data from all over the world, and get and maybe get more factors that influence the traffic accidents, and improve the precise level of our model.
Okay, thank you.
Thank you too.
Okay, so okay.
As I see no further questions, At the moment, there's no raised hands. The chat box and the Q&A box are empty. I would like to once again thank both teams for their presentations, and I think we can proceed to the second task that was given to the participants.
So for the challenge 3, I would like to ask Monte to shortly present the challenge and then invite the competitors to present their solutions.
Hello, everybody. Firstly, a short introduction of myself. My name is Monte and I'm Chief Actuary in Health Insurance Company. I'm using and exploring actuarial and mathematical knowledge on an everyday basis. And we would like to empower also students to do so in their future. I would like to thank you all accepting challenges, especially teams which finishes our third challenge reversed insurance. Name of challenge comes from fact that this challenge is a bit weird. Usually in insurance we estimate and predict claims, but here in this challenge the claims were given and we were looking for other data. I would especially like to thank Mr. Yanis Komel for exceptional help in evaluating process. Once again, you all really did a lot of effort and delivered solutions is much more that I was expected. However, we need to choose the best of the best. So selected groups for presentations are Nasi Lemak, this team with David, then team for mathematicians, team with Stipe, and also team with Thomas Rode. So I will kindly ask those teams that they shortly present their solutions.
David?
Oh, we begin. All right. So Carmen will be sharing the screen. So, all right. This has been one of our most exciting challenges yet. Esteemed judges, respected guests, and fellow attendees of the 8th European Congress of Mathematics. Hello, good afternoon, and good evening from Malaysia. I'm David, and together with my teammates, Nicholas and Carmen, make team Nasi Lemak. Now, Nasi Lemak is one of our local cuisines. It is rice cooked in coconut milk and served with spicy chili and anchovies. So, next slide, please, Carmen. From our understanding, the objective of this project is to find the most profitable reinsurance cover for the given reinsurance product, given claim size and frequency data. And this reinsurance cover needs to ensure the survival of the company in at least 99.5% of cases. Now, to find the one that was most profitable, we did it by simulating cash flows. Next. So we simulated cash flows and manipulated the chosen loss retention to find the one that was the most profitable. Next slide. Click. So for our cash flow simulation, we had to find 5 different elements that will allow us to run our projections. Claims, premiums, reinsurance claims, reinsurance premiums, and the equity available to cover our losses. So for the first, we'll go over each of these items. One slide back, please, Carmen. We'll be going over each of these items in detail of how we calculated and found them. And in the end, we will tell you guys how we projected our cash flows and what are our results. So next, we have our first item, claims, which will be presented by Nicholas. Nicholas, over to you.
Thank you, David. Hi, everyone. My name is Nicholas from Malaysia as well. Good afternoon. So first of all, we'll first find the best distribution for claim sizes and claim frequencies. So we had tested out various distributions such as gamma, exponential, Burr, Weibull, and even Pareto. And next slide, please. And click. But we found that the splice distribution between mixed error length and multiple Pareto distribution is the best among all. Next. And then, so we will first get the first splice point through visual. Next. And here we could see that there are many claims below 1000. So we will first choose around 300 as the first splice point. Next. And for consecutive splice points, we will observe through QQ plots. Next. And from this second QQ plot that I showed on the screen just now, we can see that another splice may be necessary at 6000. So next. As we choose this 6000 splice, and then we get the following QQ plot. And then you can see that from the quantiles of splicing fit, the axis there, between 2000 and 6000, there is a slight bump right there. So it would be good if we choose 3000 as another splice to actually flatten the curve. So after choosing 4 slice points, the QQ plot that we obtain is satisfactory. As we could see right there, there is only like 2 outliers, which is okay for us because most of the point lies on the straight line. Next. And then we will use QQ plot, chi-square goodness of fit test, and also KS test to further justify to test whether the distribution is suitable for our model. So in the first chi-square goodness fit test, our p-value that we obtain is 1. And so we do not reject the null hypothesis that the data comes from the described Pareto distribution. So it's a good sign for us. And as for the KS test, unfortunately, the p-value that we get is 0. And therefore, the splice distribution may not be a good fit to the data. But do take note that the KS test is not a good test due to the repeated values used in this test. Next. We will then obtain the claims frequency distribution. First, we will obtain the number of claims per month in order, and we name this as Frac. And as we could see right here, there is a residuals of fitted, after fitting the model. I mean, we will first fit the, just next for the whole slides. I think there's it right there. Next, again. Yep. Yeah, we will fit Frac using a Poisson generalized linear model, GRM, with a quadratic term. And hence, upon examining the residuals, we obtain the following 4 statistical tests right below there. And we can see from the QQ plot, that's a small point 100 right there, which is an outlier, but it's also okay because most of the point lies on the straight line. And let's look at the Cook distance plot. We can see that there's only one point which is around 0.35, which indicates that the plot does not indicate overly influential points. So this is a good thing also. But let's look at the residuals versus fitted plot. We can see that although there are like some residuals that are very, very large, like the 0.100 right there, it's around -6. But the residuals versus fitted plot, the plots are randomly scattered. So this is a good sign for us. So this model is good enough for us to use. And therefore, the formula for Frac in the Poisson GLM model, it's exponential alpha. And alpha, which is the following figure right there in the fitted model right there. And you would notice that there's an X right there. X is actually the number of months. So for example, if X equals to 1, meaning that it is the 1st of January 2012. And if X equals to 13, it will be the 1st January of 2013. And so we could use these formulas to find the most probable number of policy. So that means you can see the formula 893, which is the number of policy that we obtain from our questions. And Frac at X equals 13, meaning that we will obtain the X, which is the 1st January 2013. And for example, if I want to find the probable number of policy at, let's say, 1st January 2012. So my Frac would be from the fitted model formula, and the X would be 1. So I could get my alpha. I plug in my alpha into my Frac, and then I put it in the formula. Then I can get the probable number of policy in 1st January 2012. Yeah, that's all from me. Thank you. And I pass back to David.
Okay, thank you, Nicholas. So next we have our second element, which is premiums. Now, how do we calculate the amount of premiums we get from this portfolio? This one will be explained by Carmen. So Carmen, over to you.
Thank you, David. Hi, everyone. I'm Carmen, also from Malaysia. Hope everyone have a good afternoon. So I'll be explaining about premiums, the premium section where we estimate the most probable number of premiums and the premium per policy. So how do we go about that? Will be explained in this flow chart. So previously we had the number of claims per month denoted by a week, and it was fitted using the Poisson GRM. And from this, we will get the most probable number of policies, which was explained by Nicholas just now. And to do that, we use the concept of ratio. And this is the formula that we use just now. So once we get the most probable number of policies, we try to get the premium per policy. And previously, we do have the amount of monthly claims. And from here, we try to fit the weighted linear model using this concept of loss ratio, which is total claims over total premiums. And N here is represent the month. So let's say N is 1, so that means we're looking into loss ratio of the first month and so on. So we also know that total premiums can be defined as the product of premiums per policy multiplied with the number of policies. So we already have claims, loss ratio, and number of policies. So what we are concerned with is the premiums per policy. So rearranging this, we will get an equation that looks like a linear model, y equals to mx. And like mentioned just now, we'll fit it using a weighted linear model with the variance of loss ratio as the weightage. And we'll get the premium per policy to be 4.2223. And once we have the premium per policy, that means we can get the total premiums for every month. And we'll just take the most probable number of policies, multiply with the premium per policy, and we will end up with the monthly premiums. And so these are some visualizations of what we have come up with through the simulations. This is the most probable number of policies, and here is on the right-hand side is the number of claims. And you can see that trend is quite similar, even though number of claims is quite zigzag. And we can justify our weighted linear model to be a fairly good fit because, for example, our R-squared value is quite high, approximately 80%, which means most of the variation is explained by the loss ratio. And while the residuals plot shows a very large residuals, but the pattern is quite scattered. So overall, it's a good fit. We don't see any influential points in our data set as well. So that's why we proceed with this weighted linear model and expected number of policies and premiums per policy. So that is all from me. I'll pass it back to David.
Thank you, Carmen. So now we're going to be moving a little more quickly. The next item is reinsurance claims, and this is how it works. Next. In the assignment brief, we were told that we only have access to per risk excess of loss reinsurance, and this is how it works. For example, let's say we have 4 claims, and our loss retention is 600. That means, for example, in claim 3, when a claim is less than 600 in size, we have to cover all of it as the insurance company. Whereas for claims like claim number 2, which is very large, 1,400, the first 600, our loss retention will be covered by us, and the remaining 800 will be covered in a reinsurance claim. So this is per risk excess of loss reinsurance that protects us from large claims. And next. Since we have protection from claims, that means we also have to pay reinsurance premiums. And this is our assumption for the reinsurance premiums. Next. So we assume that reinsurance premium is our total premium multiplied by the probability that a single claim exceeds the loss retention. So this relies also on our claims distribution that we found earlier, the splice distribution. Next. Our last item is equity, the equity we have to cover our losses. So this equity, next, comes in 2 parts. The first part is 30% of all profit arising from the portfolio from the beginning, which is 1st January 2012. And the second part is all the reinsurance premiums that we pay for the same period. That is 1st January to the time of 1st January 2012 to the time of calculation. This equity is reset at the start of every year. So every year we have a certain amount of equity to cover our losses. And if the total losses for that year exceed the available equity, then we count that simulation as one where we go bankrupt. So next. Right, so we've covered all 5 items: claims, premiums, reinsurance claims, reinsurance premiums, and equity. So this is how we run our simulation. Next. So here's some values, for example. So as you can see on September 2013, our profit is equal to premiums minus reinsurance premiums, minus claims plus reinsurance claims. So you can see we have a profit, and that does not change our available equity. And you can see the next month we have a loss, which reduces our available equity. So you see when we have losses, it reduces our equity. When we have profits, we keep the profit. And as you can see in the yellow highlighted cell, at the start of the year, we calculate our equity again from the beginning to see how much we have to cover losses for that year. So we repeated this simulation 10,000 times for each chosen loss retention. And we chose loss retention in intervals of 50 between 500 and 1,000. So on the next slide, we can see our results. So between 550 and 1,000, we can see that the most profitable one in the graph on the right is loss retention of 700. And checking back to the graph on the left, we can see that the probability of surviving with a loss retention of 700 is 99.99%, which is well within our acceptable range. So in conclusion, next. The most profitable reinsurance cover is per risk excess of loss reinsurance with a loss retention of 700, assuming these 5 items: claims, premiums, reinsurance claims, reinsurance premiums, and equity, follow the assumptions and the results that we found in this project. Thank you all for listening, and we hope you learned and enjoyed our presentation. Now we open to question and answers. Next slide. Yeah, okay. Right, any questions?
I have one, Janis Kumil here. You have mentioned that the decision how many premiums earns insurance company and how many reinsurance is based on the probability that the claim is higher than retention. This is only partially true because this is the frequency of such claims, but not the severity. It's like, let's say, all of us know value at risk and tail value at risk. So value at risk say how we know the probability, but not the expected, let's say, size of that excess of that probability. Because of this, we have tail value at risk as a one measure, not connected directly with this, but the same reasons are here. So it's a good calculation if we base on the expected claims as a total, which are higher than retention, and all claims. This is only a remark, not a question in reality.
Okay, thank you, Janis. And we have looked into this and we found it quite challenging considering that the data we had available was claim sizes and claim frequency. And we are not sure how many of these claims come from the same policy. So with that, it made it a little difficult for us to calculate frequency per policy and the reinsurance premiums from that. So we resulted to choosing the probability that a single claim exceeds our loss retention. Because not only we have, when we simulate claims, we actually simulate based on past experience and not based on the number of policies that we have in that month. Yeah. So it's based on our claims frequency.
Okay, thank you. But I can say I am from old times when there were no computers and so on. We have so named claims tables, and in that tables we have numbers like here, here there were only 2,500 and so on. So if we say retention is 700, then any claim in that table was set to 700 if it was higher. And then we total both claims, original and cut it, and we get the proportion. But this was in the old time. But now we do the same, but use distributions. Okay, it's good solution.
Wonderful. Thank you, Yanis, for the question and the comment. We really appreciate it. Okay. Any other questions or comments?
So thank you for your presentation.
Okay, thank you.
Nasi Lema, or did I say it right? The name of your group. Okay, nice. Thank you, and then we can proceed with the next presentation.
Monte, you are muted.
Sorry. So we can proceed with presentation with from team for mathematicians. Thank you.
Hello.
Hi.
Hi everyone. Can you see our screen okay?
Yeah, we can. We can see your
okay.
screen and yourselves.
Okay. Okay, so we are the team for mathematicians and we will be presenting our solution now. We split our presentation in 3 parts according to the 3 assignments we had to complete in this task. And so for the first assignment, I will give the word to my colleague Sanin. So in the first assignment, we had to find the best fit for claim distribution. And we treated claim severity and claim frequency separately. And so first we made severity distribution and then frequency distribution. We were given dates and claims, and then we regarded each separately. So in order to find severity distribution, we looked into heavy tail distribution since some large amounts appeared, not frequently, but there were some. And our candidates for this distribution were power law distribution, exponential distribution, and log normal distribution. And after finding best fits in each of those distribution families, using Kolmogorov-Smirnov statistical test, we concluded that the best fit was log normal distribution. And then by bootstrapping a sample of 5,000 samples, we concluded it truly was pretty good. This is how our fits, how we fitted the data. So here on this plot, we can see cumulative density function for power law, for log normal and exponential. And we can see that the tail of exponential actually begins very late. It doesn't exist till like 5,000, while those two begin sooner. And the statistical test told us that log normal was our best candidate. And when modeling frequency distribution, we were making a model that will predict how many frequency we expect, how many claims we expect to have in each month of each year. When looking at the data, we saw that our variance was much larger than the mean. And this suggested that it could be a negative binomial distribution. And our other candidate was a Poisson distribution. However, Poisson distribution is usually used when variance and mean are approximately the same. And using chi-square statistical test, we also concluded that negative binomial distribution was the best. And later we'll use this to model things. Okay, that's all from me. From now, my colleague Anna will talk to you.
Hello, everyone. My name is Anna, and I will explain our solution to the second assignment. Okay, in this assignment, we shall find the most probable number of policies in the portfolio for each month. We divided our solution into 3 parts. The first was to estimate the average premiums for each month. The second was to calculate the most probable number of policies. And the last was, of course, understanding the given results. So how did we estimate the average premiums? We estimated the first one by dividing the sum of claims given in December of 2012 with the most probable amount of loss ratio and the number of insured persons at the end of the month. That was given in the task. After that, since the average claim grew with time, it was sensible to assume the same is true for the average premium. For that reason, we fitted a model to find the inflation rate of the average claim and use the same rate to increase the average premium value. The model is given on the presentation, and by taking the logarithm, we got the relation above, which meant we could fit a linear regression model, and then we easily found the inflation rate. Next. After that, we were able to start calculating the most probable number of policies. We did that by using the Monte Carlo simulation method. As you all probably know, loss ratio is computed by dividing total losses by total premium. In our case, losses are fully covered by the sum of claims. So in each simulation, we calculated the total premium for each month by taking a random value of loss ratio distribution. Then we get the number of insured persons by dividing total premium by the average premium. After 1,000 simulations, the estimated number of insured persons should be somewhere around the empirical mean. Finally, here are our results. The graph shows the monthly number of insured persons. At first, it was surprising to see such a fluctuation on the graph, but we can explain that. So the number of insured persons in the current and previous month are related only to the variance of the loss ratio. And as you can see, that cannot provide us with enough information about their connection. And also the exact numbers were given in our Word document. And that's all from me. Thank you for listening. Stipe, you can continue now.
Okay, so the remaining task was assignment 3, in which we had to find the optimal reinsurance cover for our company. So let's first look at the assumptions which were given in the problem. So the first thing was that the only kind of reinsurance we were allowed to look at was per risk excelling reinsurance, which, as we all now know, means that we only have to pay claims up to a certain predetermined threshold, and everything above that is dealt with by the reinsurance company. Another assumption was that our equity was based on the reinsurance as well as the profits from the previous year, which means that the amount of reinsurance we need will also depend on the profit of our company. And we also had the ability to change the cover every 3 years, which was quite important in our modeling approach. So, for example, just to be clear, we could have a situation where in the period from 2013 to 2016, we have a certain reinsurance cover. After that, since 3 years have passed, we are allowed to make a change if we need. And the same can be done 3 years after that. And we have 2 small examples here. And from this, we can see that the 2 things we basically need to find to create a good reinsurance strategy is the optimal times in which we will change the cover, as well as the optimal covers in these small intervals. And that is those are the 2 components of our solution. So for the first component, let's assume that we are trying to find the optimal insurance cover for a smaller time period, like 3 or 4 years. So the cover is basically determined by the threshold above which the reinsurance company covers our losses. We were supposed to find such threshold that ensures 99.5% probability of survival. So how did we do that? Well, for a given threshold, we can find this probability by doing Monte Carlo simulation, as we have created a model in assignment 1, which models both the frequency and severity of claims. So we can test whether with that
with our distribution, with that threshold, our company would survive. Now that we know that, finding the optimal threshold is simple by using binary search. We can basically find an interval in which the optimal threshold surely lies, which will be like from 0 to a very large number, which is not even realistic. And then we simply look for the optimal value. After we find optimal values for those small time periods, we now need to look at the strategy of changing covers, which years we will change our policy. So the good thing is that we had actually a very small number of combinations, as our period was only about 10 years long, and we could only make changes every 3 years. And we also could assume that if there was a large time period in which we made no changes, it would be better to make one. So obviously 2 different covers for the first 3 years and the second 3 years will be better because you can be more accurate to the data of that time. And that basically left us with 2 possible strategies we could use. For each of those, we simulated from our distribution and found the optimal thresholds. And then we compared the profits which we would get from each of those. And the one that was better was chosen as our optimal reinsurance policy, which was given in our documentation. And basically that would be that. If you have any questions, we are listening, and thank you.
I can see hand from Anna, so Anna, please do not hesitate to ask.
No, I won't. Thank you. First, I need to admit I haven't gone through your codes, so I was just reading your report. So eventually my question might be, let's say, incorrect or explained in the codes, but I would like to see or to hear something that basically Anna presented with the log model. Okay, so you had this discussion that the average claims grow with time. So you were estimating the inflation rate, which would be in economics, the growth rate, right? So I want to know why you haven't included a linear trend, for example, or a kind of trend in that kind of regression modeling, or how can you convince us that it's not a spurious regression that has some kind of stationarity problems? Thank you.
So basically, the way we looked at this problem was we assumed that there was some sort of inflation rate which our values would be multiplied by each year. For example, like the inflation is at 1.001%, and then each year you multiply money by that amount. And this model, when you take the logarithm of it, you actually get a linear model. So it does create some sort of linear trend. But we simply defined it by multiplication, as we thought it was more like understandable in financial terms to have like some sort of number that is a bit bigger than 1 that multiplies the values. But in the end, the creation of the model was a linear model. If that answers your question.
Okay, so if I've got it correctly, so you got y and b as variables, right?
Yeah.
And then you were calculating what an x, right? Was that, did I grasp it correctly? Because I mean, in the reports, there are not that many details about it. So I wanted to ask you in person. So assuming that it is a time series model. So if things grow together, so there might be like an issue of spurious regression, which was not explained here. So like usually the trending data, whatever it is. So, but I will need to go to the codes or ask my colleagues who went to the codes what in specific you have done there, if there is an issue with the trend. Okay, but thank you for your answer.
Thank you.
Okay, I can see also a question from Malaysia, so please, David.
Hi guys, this is a question, I'd say one competitor to another. How did you guys determine the amount of profit in the first year? In that, since the loss ratio was given for the second year onwards, what assumption did you make to find the profit in the first year, which will give you equity at the start of the second year?
So I think we at one point asked the organizer this question, or you actually asked it, I'm not sure, and someone told us that it would also be okay to use the same loss ratio model for the first year. However, in actually calculating it that way, we would get like a very small starting equity. And in some of our simulations, we got some weird results requiring us to have very large reinsurance policies in order to ensure our survival. So we also looked at some models where we gave our company some sort of like boost at the start with some larger amount of money, which we would have to see how the reinsurance policy would change if we had some more equity at the start.
Okay, I understand. Thank you. Because we did face some challenges, especially before we made that assumption where we were going bankrupt in the first year before we had our reinsurance.
Yeah,
so
yeah, it was pretty much
that assumption really helped. Thank you, Monte. All right, so that's my question. Thank you.
Thank you. Any other? Or if not, then we can move to the last presentation, which is from with Thomas Rodell, right?
That's right. Do you see my screen? Do you hear me?
Yeah.
Yes, we can see and we can hear.
Okay, thank you. So my solution to the reverse reinsurance problem is the following. Firstly, okay. Yeah, the same as the previous groups, the assignment was divided into 3 parts. First, we had to fit the distribution. Then we had to calculate the number of insured from a loss ratio, and then to develop an appropriate reinsurance scheme. If we first take a look at the data, we see that we have on the left, the size of claims is a heavy-tailed distribution because we have some quite high density of quite high values, and that the plot of the frequency of claims by month is increasing. So these are 2 things that we will look into in the next slides. So first, finding the distribution of the size of claims, we tried fitting different distribution using the maximum likelihood estimator and the method of moments estimators. And we found very different results using different methods. So this is a sign that that I found a bit alarming. If we see that the different methods don't give us the same results, we're not surprised with this next slide that these tested distributions failed the Kolmogorov-Smirnov test, and we cannot reasonably assume that the results come from the tested distribution. So what we did was I switched to the empirical distribution, which is of course a case of overfitting, but it seemed to work with the data and it passes, of course, the tests. But just to mention what could be done to make this better, of course, we can see here that we have some bins. We have a bit. I believe that we have a bit abnormal data where we have some bins that are very frequent next to some bins that are a lot less frequent. Maybe a smoothing out of this distribution could help. So if we could transfer, we believe that maybe there was some rounding done, or the nature of the claims is such that some smoothing of the distribution could prove fruitful. Yeah, so this is something that we could improve on in the future. So for finding the distribution of the frequency of claims, we believe it's not reasonable to assume a common distribution for all data points, because we saw that, well, they're increasing through time. So we believe that the first data points come from a totally different distribution from the last data points. And we attempt to connect the data in yearly intervals. The solution we propose is a Poisson distribution per month, where the parameter lambda is given with the average of claims realized in the running year. So not the calendar year, but the running year. But with this assumption, we cannot run the same tests that were done for the severity of the claims. And here is a graph that shows the running yearly averages and the frequencies. So these here are the lambdas that we use in the Poisson distribution. And here is an example of one simulation of our frequencies and the observed frequencies. So we see that it fits reasonably well, and the same can be said for cumulative monthly claims from both the frequency and the severity of the claims. So the next part was finding the most probable number of insured. The assumption that we made here is that the ratio of the yearly average of number of claims calculated from the distribution of frequencies to the number of insured people is constant throughout the whole period. And from this, we calculated the most probable number of insured, and we got the sum of monthly premiums as the expected value of the monthly cumulative claims over the loss ratio. This gave the following results. At first, we have around 260 insured persons, and the premium is quite high, around 7. And at the end of the year 2020, we already have around 5,000 insured people, and the premium decreases to about 6. I believe this slight reduction of premiums seemed sensible because of the increase of number of insured people. This is beneficial to the pool in the form of reduced variance. So we didn't assume that the premiums are constant throughout the whole period, but we believe that is a reasonable assumption, and it also helped with the determination of a reasonable reinsurance claim, because as the previous teams have mentioned, these 4 first years are crucial in the determination of the reinsurance claims. So for finding an appropriate reinsurance cover, we assume that we have, for the coverage of losses, 30% of the equity from the previous year plus yearly profits. And we assume that the equity available in the first year is that of the average year of 2012, so as to make sure that we survive that year previous to our reinsurance game, as the previous teams have mentioned. Then the survival function, we determined that if the claims exceed the capital available for coverage, then the company doesn't survive. And we calculated the insurance premiums as the share of premiums that corresponds to the amount covered. So the expected value of the claim over the given reinsurance cover. And this splits the premiums that we got in the previous assignment, so in assignment 2, into 2 parts. One that is for the insurance company and one that is for reinsurance company. We tried the following. We tried the following reinsurance cover and got the best results. If the first period we have 730. And then in the second and third year, we can increase this reinsurance cover, as we said, because the first years are the most crucial. So in the second period, we have 2,000, and in the third period, we have 3,000. We tried 1 million simulations and got that the survival to the year 2020 is exactly 99.5%. And the average profit of the insurance company is about 100,000 euros, and the average profit of the reinsurance company is 250,000. And this is what we calculated just to make sure that the deal is okay for the insurance company also, but we don't go into the risks of the reinsurance company in this. So this would be the solution I presented. If you have any questions, please do ask.
Okay, so it looks like no questions or any changes. So then we can go on with the last challenge. Thank you everyone for presentations.
Okay, I suggest that we have a 5 minutes break, and then we continue at 1:30 with the presentations for the fourth challenge, and the challenge will be presented by Rudy Lipowitz. Thank you. So welcome back, everyone.
Hello, can we start?
Yeah, so please.
Okay. Hope you hear me well. First, kind regards from currently overheated Slovenia. Thank you for involving in the contest. Short description of the challenge. We have provided data about the MTPL, Motor Third Party Liability Portfolio. We have provided the exposures with certain attributes and the number of claims. We have split the portfolio in two parts. One was the learning part, from which you should learn as much as possible. And the challenge was to predict the number of claims of the other part of portfolio. First, I would like to emphasize that we didn't have theoretical probabilities, but we have compared two observed probabilities. The task is kind of holy grail of MTPL line of business, because as we all know, it's one of the most developed and matured line of business, and the one who better allows for different premium factors is the winner on market. Now I would like the contenders to do the presentation of each challenge. So I suggest that we start with Mr. Koch.
Thanks, thank you very much. Okay, so maybe I'll share my screen. Can you all hear me?
Yeah.
Good.
Yes, we can.
So I'm gonna try my luck with sharing my screen. It worked before, but okay, so just give me 1 second. Yeah, there we go. Is it fine?
Yeah.
Okay. Yeah. Okay, so hello, my name is Jonathan Koch. I'm a student studying at the École Polytechnique Fédérale Lausanne. And today I'm very happy to be here to speak to you a little bit more about my solution to data challenge number 4. So I'm from Team Correlation. And firstly, I would like to say thank you to the organizers. Thank you to the Slovenian Insurance Association as well for, for the kind guidance in this challenge. Okay, so before I start, I really want to just start off with some of the thoughts that went through my mind as I started to look at the data, okay? And the first admission, the first very honest admission here is that I have actually little to no experience in insurance count modeling, right? So this was relatively new for me. My training is primarily coming from statistics, which is of course highly relevant here, but like all applied statistics, my goal here was to first familiarize myself with the problem at hand, right? So with that in mind, I was approaching this challenge purely from a statistics kind of point of view, right? And the first question is to do with model validation, right? And this is pretty essential because I wanted to know, because I need a model validation set to tune my models appropriately. And if the distribution of covariates in the test set were to be different from the training set, I would then need my validation set to appropriately reflect it, okay? So I need to construct my validation set from my training set, right? To get a proxy of how my model does on the test set. But luckily for us, I found actually not much significant difference. between the distributions of covariates in the test set and the training set. So it seems like at least the test set was, randomly left out, right? So, and there's no missing data as well. So for example, for the covariate F13, we see in the test set and the training set, no noticeable difference with the distribution of the number of zeros, ones, twos, etc. And the same is true for other categorical variables like F12 or F3, which is an ordinal variable. And the consequence of this is that model validation, this is the consequence from a statistical point of view, is that model validation is pretty easy. Since the test set seems to be randomly left out, we can do random sampling, okay, subsampling of our training data, or we could do some sort of random k-fold cross validation, which is kind of what the approach I took, right? In particular, I took like a 5-fold cross validation, so big K equals to 5. So how it works, I'll come back to this later, is that I split my training data into 4/5 training data, 1/5 validation set, okay, randomly. And then of course, without any partition, right, I trained my model on 4/5 of the data and then left out 1/5 to do my validation, okay? So then in the end, I have 5 validation scores. I can take the average, and this will give me a proxy of how this model does on the test set, okay? And this will be very important later. Now, I mentioned that I don't have too much knowledge with claim count modeling, but it seemed pretty obvious, at least by just looking at exploratory analysis of the data, that exposure is the only covariate we know anything about. So can we do anything with this? So it's pretty obvious that the higher the exposure, the higher the claim count. So the approach we took is to take frequency divided by equals to count divided by exposure, right? And normalization seems to be really, really useful here, which makes a lot of sense. What this means, of course, from a model consequence point of view, is that this is simply the offset in the linear predictor when I do my modeling. Okay, when I look at the counts, I can just do an offset. What this means concretely is that if you look at the log of the expected frequency, so the expected claim number divided by exposure using the notation from the data set, I would just want to model it as a function which I need to learn of my covariates. Okay, so the covariates are, the F3, F12, etc. Right? What this means is, just putting it on the right side would just be an offset term, offset of the log of the exposure. So if we model the log of the expected claim counts, which is very common link function, we would just have the target function plus some offset, okay? And this target function is something that we want to learn in this case. Now, a quick Google search will tell you that the gold standard for claim count modeling is the Poisson GLM, Poisson GAMS, right? And so I wanted to kind of like try to stand out in this modeling approach. And also I saw like some potential problems, right? The first potential problem is that, it was the name of the game. We didn't know anything about F3 or F13, right? That was just the game, that was the competition. But because of that, we have no knowledge of the covariates. We have no knowledge of which ones are important, no expert knowledge at least. And if, those of you who know more about GAMS, which I'm sure all of you know about GAMS and GLMs, you need to choose an appropriate basis, right? So how about potential interactions? Do we need, what kind of tensor product spline would we need to use, or cubic spline if it's just in one direction? So the model consequence of this is that I somehow needed a way to perform feature selection, so covariate selection, without actually knowing what the covariates are, because I don't know what F3 is, F5, F13. So the approach I took was to do a very simple approach of just having lasso or boosting methods. And the same problem was also there for incorporating interactions between covariates, right? And the approach I took, there are many different ways to do boosting, and the approach I took was boosting of regression trees, okay? And that's something I will focus on in the next slides. So I'm halfway through my presentation. So as an exploratory analysis, remember, looking at normalized counts is of course important. So if you look at the average normalized, by exposure claim counts, essentially what we're interested in is just to model the residuals after taking into account the log exposure via this offset that I mentioned, right? And clearly there are covariates which are important. Okay. In this case, as the covariate F3 increases, the average normalized claim count also increases. And you can see that there's a jump somehow around, above 14, okay? And the same is kind of true when you, with some other covariates like F13, for example, but, in the other direction. Okay, so before I go into, something about boosting trees, here's a little bit of a crash course. We somehow need to know, before we do boosting, we need to know about what a tree is, okay? A tree is, as the name suggests, like a tree, right? You have leaves and it's at the end of the nodes, and then you have your nodes and you have branches of the tree, okay? So a tree, I think, is best illustrated by this example with just 2 layers, okay? And in this example with 2 layers, if we just focus on the essential information, I'm going to cover out the other information, which has to do with information gain. But on the first node, what you do is you choose which covariate, okay? You choose F3 in this case, which is one of the covariates. Okay, we choose F3. We've seen this before, F3. Okay, and then after you've chosen the covariate, you choose your decision, less than 2 or more than or equal to 2. If it's more than or equal to 2, it goes to the bottom node. If it's less than 2, it goes to the top node of the tree, okay? That's how a tree works. And then in the next layer of the tree, you then do the same thing. You repeat the same process. You choose a covariate, and then you choose a decision, whether it's less than 2 or whatever, in this case. But these are for ordered variables, okay? I'll explain how to do it for categorical variables later. Now, that was a tree with a very simple example of just having 2 layers, but you could have a tree, a more complicated tree with 4 layers, 5 layers, 6 layers, for example. And I didn't tell you how to train a tree, but if there are different ways to train a tree, you could train different trees, okay, with different covariates in each level, okay? You could train, many different kinds of trees. And all these kind of trees that you can potentially train, it's in this infinite dimensional space called the space of regression trees, okay? Okay, this is important when we talk about boosting later. Boosting regression trees is simply, okay, taking a linear combination of fk, okay, as a function of covariates, and these fk are simply trees, regression trees, okay? More precisely, what is this y hat here in the machine learning notation? In our case, it's just this target function here, which is the function of covariates that we need to learn, okay? Then we're taking linear combinations, additive functions of our trees. And to remind you what this F squiggly is, it's just the space of regression trees, okay? So I haven't talked to you about how to do this, how to learn, right? But so gradient boosting, in other words, learns the set of functions, right, used in this model. So whether or not it's which tree to use and how to grow the trees. And in the end, you will also see how to choose the number M here of trees. Gradient boosting does this by minimizing some regularized loss function, okay? So now, no pun intended, but here's a crash course on loss functions. In machine learning, it's about an objective, minimizing an objective, right? Which is to do with a combination of loss function plus a measure of complexity of the model, right? In this case, our loss function, is something we have to choose. And if you look at the, fitting well to the training data, so it's a function of the training data, at least gets you, hopefully close to the underlying true distribution, right? And this here is a measure of complexity to, discourage overfitting, right? So simple models, it encourages simpler models, let's put it this way. So in a simple case, which we all know of rich regression, right? We have here in a linear setting, okay, it's just a, linear combination of weights. The penalty would just be the L2 norm or the L1 norm, okay? Simple, right? And in this case, with the linear rich regression, linear lasso regression, implicitly, actually, you've seen this formula before. This is just linear, squared loss, right? But in counts, when you're modeling counts, there are other loss functions which are perhaps more appropriate, right? Because the counts cannot be less than 0, so for example, right? It has to be necessarily positive. So just to remind you, if we use boosting, this is our, our target function. And this is the Poisson deviance loss that I used in this competition. I also use other loss functions, which I had to code by hand and, find the gradients and the Hessian by hand, but, it didn't seem to actually lead to much improvements. I will explain why maybe in the Q&A. Now I'm running short of time, but in the last few minutes, I also use such stuff like the gamma loss and the Tweedy loss, okay, which have both been shown to be actually very good for different situations, right? The gamma loss actually is well known for claim severity modeling, and the Tweedy loss for like handling overinflation, zero inflation of counts, right? So we have all these ingredients now in our backpack. Okay, so this is just doing the lasso, which I briefly mentioned before, but I want to focus on the boosting models, and I fitted it basically by minimizing this objective function, okay, based on what I choose for the loss function, okay? In this case, it turns out that the best one was the boosting with the gamma loss, okay? Now, how did I get this 0.0033? I'm sure it was a lot of information. So this 0.0033 is, gotten from my average 5-fold cross-validation score. So in each training each fold, I fit this boosting with with gamma loss on the training set, and then left out this one. And then I calculated the score, the test score, basically, that was given to us, okay, as a measure of performance on the test set. And this was the exposure, because it's weighted by the exposure, it's squared loss weighted by exposure. And then that's what I did. And to choose the number of trees in the model, I just chose to stop adding trees in as I reach like a plateau or a valley, you know, with the test error, okay? Right, and that's how I got this 0.0023. Okay? That's how I chose my model. So other remarks here, which I don't have too much time to go into, but I promised you I would go into how I would do categorical variables, just one hot encoding. That means it's a 1 or 0. You know, 1 or 0 if it's this class, 1 or 0 if it's this class, and a tree can easily, you know, there are two splits, so it can be 1 or 0, 1 or 0, right? All the loss functions were weighted by exposure, and I used some sort of a Bayesian optimization scheme to choose hyperparameters. You know, there are many hyperparameters in the model, such as, you know, how many layers each tree should have. The beauty about boosting is you get actually a variable importance measure, right? And you can see this variable F3 here is pretty important, okay? Then exposure also comes next, and there are other variables there. Now, visual inspection was just a really quick way to see, okay, how my model is doing. Is it high when it's high? Is it low when it's low for the training set, okay? But it's important that, you know, it doesn't look like it's overfitting because we don't know what the test set is. But this was a way, at least just to see, okay, my model is doing all right. So here are some references. I think I've exceeded my time. Thank you very much for your attention. And thank you again for the organization. This was a very fun conference. And I wish I was in Slovenia, even though it's very hot now, apparently. Thank you.
Yeah, thank you. But we are by the sea, so if it's hot, you can go swimming. Yeah.
The beach, I guess.
Yeah.
Thank you, Jonathan. Any question? Otherwise, I have one. Did you find also any other, or come to the mind any other measure for measuring the quality of the model?
Yeah, so I mean, there are other, so for example, instead of using, for example, in this case, here I told you the measure that I used was the one given by the challenge, right? Because I knew, you know, this was our measure of performance. But instead of using, you know, something like this weighted by exposure, instead of using the squared loss, right, one could perhaps use something more appropriate for counts. Because if you look at this, if you look at the squared loss, I mean, the y hat could technically be positive, negative. I mean, there's no reason why you could predict a negative count. But of course, it will give you a bad score because, you know, this will never be positive, negative. But instead of using the squared loss, there are also other measures. You know, squared loss is also kind of implicitly assuming some sort of normality if you are having a continuous distribution. So instead of that, you could use maybe one of these other loss functions instead, weighted by exposure, of course. You know, maybe for example, the Poisson would be appropriate in this case as well. But it really depends, of course, on the kind of risk measure you're taking from your company, right? Yeah, what do you deem as maybe, I don't know. That's just, it just depends on the risk aversion of your loss function as well, right?
Thank you. Any other questions? Okay. Then I would invite Enei to present his solution to the challenge we have done.
Yeah, I will share in a moment. Do you see the screen?
Yeah, thank you.
Yeah, so first I would like to thank you for the invitation to the final round. It's a pleasure presenting the solution here. So first, if we go to the challenge, so what we actually need to do. So we got, like already Jonathan mentioned, we got the training set where we got the exposure and the number of claims for some different combination of risk factors. And then the goal was to estimate the number of claims on test data where we only had the exposure and risk factors. And some insights about the data. First that we notice is that the test set is quite, it represents 45% of whole data, which is quite a lot. So we needed to be careful not to overfit. But as already Jonathan mentioned, we also checked that the sets were stratified. So the same percentage of certain variable was actually present in the training and test data. Maybe the biggest difference was with the exposure, but minor differences. Then the second thing was that we had many observations with 0 claims, actually almost 87% of the data, which is quite a lot. And we can also see that here on that graph, the first beam stands out there. But if we zoom in here, we can see that we can also find claim numbers also here, 150, 140. But this, of course, depends on exposure. So here we are just looking at the number of claims. But the most of the observations are somewhere here, with 0 claim almost 40,000, as we can see, and then the 1 claim 10 times less, almost 4,000. So with that in mind, we tried to model something, but because of the very specific data, we just tried to make like very trivial predictions, so just to predict all the time the average to get some benchmark. And with the average, because the average is actually the constant that minimizes the mean square loss. So if we just predicted the average, we got the error, mean square error, a little bit less than 7, which may, if we are looking at we have, let's say, 120 claims, and then you predict 115, it may look good, but in that case, it's not quite okay. But then, we also know that the exposure is we expect the linear dependence with the exposure. So if we do very simple linear regression, so just to predict just with exposure, we get much lower mean square error, which is, let's say, whatever we will do in the following, we need to be better than this. So next, what we've tried to do was, because the challenge was that kind that, we just got data, we didn't know what's happening. So the first thought is that we just tried few algorithms. So we used some machine learning, some popular machine learning algorithms, and the best were neural networks and random forests. And actually those 4. So neural networks and random forests, and gradient boosting and extreme gradient boosting, which are just it's supposed they are, I don't know. Here we have some trees, and here some information from some trees are passed to the others when they are learning. So they are supposed to be a little bit better. What we also found out is, as also Jonathan mentioned, it was a little bit difficult to work not knowing what some variables are. We considered that we tried to actually transform all ordinal variables to categorical. which actually produced most of the time better results. So usually, in most of the cases, we stick to it with it. But then we also needed to tune the hyperparameters. So they are called hyper just because they are one stage higher than the parameters we usually think of. Because let's say the same algorithm can work very differently with different settings. So with those hyperparameters, we somehow set those settings, and then when the model is learning, those basic parameters that we usually think of are determined. Yeah, so those parameters are determined based on hyperparameters. So, and there is no ultimate setting for all the algorithms. So when we have specific data, we need to tune the hyperparameters. And one way to do it is to just set the combination of hyperparameters that we will try, and then we see what settings are the best, and then we choose those. But when doing this, we try to do something a little bit smarter, and it's a procedure where you define the space of those hyperparameters, so the settings of the algorithms. And for example, if we take neural network, yeah, we would define number of hidden layers, number of neurons in every layer, penalizing term, learning rate, and things like this. And then the algorithm is looking randomly through that space and evaluate the algorithm based on the settings it chooses. And we need to specify here some function, so some loss function that we want to minimize. And then the algorithm remember the settings and the loss function. And at the end, so we can try this 1,000 times, and at the end, it will give us the best set of hyperparameters, so the best settings for the given model. And yeah, I mentioned that it's searching random, but it's also, yeah, maybe it's just a little bit smarter because it remembers where the settings produced, so which settings produced good results, so which we can see somewhere here. And then the algorithm try to sample around those that point a little bit more than the other space. So this was the, yeah, so we tried almost all machine learning algorithms, but then at the end we tried very simple one, probably the most basic one that if you Google, you see, you Google count data, you get generalized linear models. And here we were trying the zero inflated models, hurdle models, and Poisson and negative binomial regression. So all of them produced somehow similar results. Maybe the hurdles were a little bit worse. But because of the simplicity, and I think that it's easier to understand, the models we choose to proceed with the Poisson and negative binomial regression, which is actually, we want to make something, a link, something like this. Yeah? So we are modeling the frequency with some link function, which is here the e to the power of this. Yeah? So if we take logs of this, okay, we get log of frequency, and then the simple sum, which is also in the basic regression. And I think that already Jonathan mentioned this before. Here the exposure is offset. So when we take logs and put the exposure on the other side, we have offset log of exposure. And here the algorithms, when they are trying to estimate those parameters, they are minimizing some specific loss based on Poisson or negative binomial distribution, so depending on the model. And this actually produced almost 2 times lower mean squared error than the basic linear regression, and it was also better than all of the machine learning algorithms we tried. Maybe the neural networks were close, but still worse. Yeah. But yeah, we still think that there is a place for improvement in neural networks and also in other machine learning algorithms. So here the possible improvements we already mentioned in the report, that the best would probably be to identify some correlations between the variables that we would model. But then the second one is that we would somehow implement the costume loss in the neural networks or other algorithms. And so here we have, for example, the neural network, where we'll have one layer of inputs. So these are our pricing factors. And then here the next layer, but now only the one neuron is shown. And what is happening here in that neuron, we just get the linear combination. So weighted linear combination of those values of those neurons, and the weights are the weights given on that connections. So here we get something like in linear regression, and then based on that and some activation function which can be determined, we get the output. And here we compare it to the actual output, and we see where we are. So we see the loss, and based on that loss, the loss somehow travel back, and the weights are updated, and this is happening until the process converge. So if we would somehow implement that log link that we mentioned before, so here that we would so if we take log here on that equation, we get the sum. So this sum, which is the same as sum here, yeah. So we would get that log link, and then we could also implement the custom loss function, and weights would be updated based on that. And maybe we would get better result, but we were a little bit short on time, so we didn't succeed in this. But so let's say if we take a look linear regression, the mean squared error was a little bit over 0.6, and the neural networks came down to almost 0.4. So maybe with the specific loss function, it would be even, I mean, it would probably outperform the negative binomial regression, but yeah, maybe in the future. So yeah, actually now when we were talking about the loss, so only one layer and one output neuron should perform somehow like our binomial regression here, but we can also add many other layer, so hidden layers here in between, so it can perform even better. But so this is maybe the sensible thing to do if it brings us great reduction in the predictions. I mean, a great reduction in loss for predictions. But on the other hand, we would not understand almost anything. Yeah? So that's why we still believe that the model we presented, it's reasonable, because we have very simple formula, and because we transformed all the variables into categorical. Those x's are just zeros and ones, and once we estimate the values, so let's say this is intercept where everything is hidden, so the base example, and then if we have for f1, let's say p, we get the value something like this, and if we take a look what is happening here, if we put this So if we put e to the power of that value, we see that it's higher than 1, and it's actually contributing positively to that ratio, so to that frequency. So we can see which variables are decreasing or increasing the frequency, and we can more understand the connections. So here, if we'll take, for example, one specific combination of risk factors, so something like this. What we estimated, yeah, you need to believe me that those numbers are correct. But we would estimate something like this. So this is the number of, this is what we want to predict. We divide by exposure to get frequency. And then we put all this to the power of those coefficients here. So if we remember this one is the intercept. So here the intercept. And yeah, the others are based on those coefficients. And in that case, yeah, we get the predicted number of claims to be 9.81, which is quite close to the real number. So let's say here 10. And so we can say that with this we have a transparent model that is very easy to use, easy to understand, and it can be implemented in few lines of code. And also, if we take a look at that picture, we can see that we have, let's say, quite solid predictions. Maybe here, close to 0, the real data is a little bit more dispersed because of the noise in the data. But here, if we take a look, this looks quite close. Yeah. So yeah, we believe that this somehow justifies the choice of the model. So that would be all from my side. And if you have any questions, yeah, feel free to ask.
Maybe just one short question. Have you maybe investigate also interactions between covariates?
We tried with some data transformation, but it didn't prove to be fruitful. But on the other hand, here when we, if we transform everything into the categorical, we have for maybe it's a little bit, there are a little bit more parameters, but we have for every parameter certain value, and we can,
Okay. Thank you. Jonathan.
Hi, Anuj. Thanks for. It'd be nice to talk to you after the competition. Similar stuff. Yeah, but I wanted to ask you actually about the performance of your your neural network while your random forest and boosting. I mean, I would expect them to perform rather similar, right? Also, random forest boosting. I mean, they're
actually, okay. Random forests are really easy to use because probably the most important parameter to set, hyperparameter, is just number of trees, and usually the more trees you have, the better the predictions will be. So gradient boosting and extreme gradient boosting were a little bit more difficult to use. So sometimes, they produced very bad results, but when we tuned the hyperparameters, they were much, actually, forests were about 0.6, a little bit less. Then extreme gradient boosting came down to 0.55. So this is everything in terms of mean squared error. And the gradient boosting was actually the best from those, and it came down to 0.5, maybe a little bit less. But then the neural networks outperformed them, even with no log link or the specific loss function. But then GLMs, we found, we got something like 0.36 or something like this, which is better.
I mean, if I could just say something, I think if I got it correctly, I think when you presented on the neural networks and the gradient boosting and all, did you use the log exposure as the offset?
I didn't know.
Yeah, I think that, I mean, for me, I also, at first, I did gradient boosting and all that without the offset, and I had, you know, bad performance as well. I think I think the key is just to use the log of the offset exposure as the offset, and then you're just doing the residuals instead of the claim counts. Because if you use trees, for example, it will struggle with the exposure.
Yeah.
Less than 1,000, and then it will freak out a bit, I think. I think, I mean, I don't know if it will improve in your setting, but this may be my
yeah, it's true. But yeah, we were trying just, I mean, we were also trying a little bit, but just a little bit with the log link, and it didn't go well at the beginning. Probably we would need to specify the cost and loss. Maybe then it would work better, but with mean squared error was, yeah, didn't work well. But even if you just put in the raw data, it looked okay at 0.5. I mean, it was still, yeah. Thank you.
Thanks.
Thank you, Renee. Any other questions?
I think that someone is raising hand.
Guyen?
Yep. Yes, I have a question. In your last figure, I'm not sure if you had trained the model in the training set, and then you just predicted in the same training set, or is another validation set? I'm not sure, because
yeah, this is also one beauty of those models, that we know how they work. I mean, okay, we know how also for the others how they work, but okay, here we are setting some parameters, so for all pricing factors, and you can fit it on the whole data, and then get the fitted values, and the fear for overfitting, it's much lower here than it would be with neural networks, because here you have those 20, 30 parameters that you need to estimate. And yeah, so if you just, like linear regression, when you take fitted values, you won't overfit probably.
I'm not sure if I understand your answer, because my question is just that the results that you saw in the figure is it the training set, or is it another?
Yeah, it's actually the whole training set.
Okay, so
because yeah, because
so in my opinion, it's not validating at the result, because you need to validate it on another set. So the will,
I mean,
just objective.
We
maybe meet with the problem of overfitting, and you know that, right?
That's what I was trying to explain.
Yes.
Because of course, yeah, for machine learning algorithms, those neural networks, forests, and everything, we of course divided when we were tuning the hyperparameters. So let's say here, we specified the score, which so this is quite computationally, yeah, it's quite expensive process. Yeah, it takes a lot of hours. So what we've specified for, I mean, what is probably reasonable to specify for that loss function that you minimize, is that you split the train data. So the train data where you know the outcomes, yeah, we split it to the 3 or 4 sub data, yeah, and then you make cross validation, and you take the average of those 4. So here you know the you are actually validating on the data where the algorithm don't learn. But if you do this with the so generalized linear model where you have some parameters, that is not such a problem. I mean, of course, we tried when searching for the loss, we also divided the test to the train, so the train data to 2 sub data, so to the subtrain and the validation. And then you make that prediction, but it's, you know, when you have 20 parameters to estimate and 40,000 observations, you probably won't overfit if those parameters determines everything. And also the loss, if we take a look at the fitted values, or if you fit the model to the sub data and then you validate it on the somewhere where you know the loss is almost identical. Yeah? I mean, maybe sometimes even lower where you are afraid of overfitting. Actually, in the other case, yeah, sorry. Yeah, thanks for your question.
Okay, thank you.
Thank you. So this is, yeah.
Yeah, I had a question for you, Rudy. I'm just wondering, in a normal insurance setting, are you always given the exposure for the test set? Like, for example, if you want to predict from the test set, are you always given the exposure, or is it depends on the type of application? Because I'm just wondering if there is a situation where, you know, in the learning set, you have the exposure of each claim count and you have the number, but maybe perhaps in the test set, you actually don't have both. You don't have both the exposure or the claim count. Because in this case, in this challenge, we had the exposure as well. But I'm just wondering if there's maybe this kind of, I mean, what's the difference, and maybe in which situation you have one of the other? Does it make sense, my question? Really?
It makes sense, yes. It makes sense because you never get the whole combinations. The most portfolio consists of just one exposure of one, so it's a unique combination. So we never know what will be in advance.
I see. Right. I see. Yeah. Okay. So I mean, in reality, you wouldn't have the exposure, and then you couldn't use it for your model, right? You couldn't use it for the model. You can only use it as an offset, or as you multiply that with the frequency to get the claim count.
Yeah.
Right. Okay. Yeah, I found this challenge a bit unique because we also had the exposure, so somehow we could use that in a way. But I was just wondering in the business side, what it's normally like, because it seemed unrealistic to have the exposure beforehand. I don't know. But yeah, anyway, so thank you.
You're welcome.
Okay, so we have finished with the presentations and the questions. So the committee will meet on another platform while you can continue chatting. So see you after, I don't know, 20 minutes to half an hour.
Okay, so we leave this link completely, go out together.
Yeah, maybe this would be advisable. Giga,
yeah.
I assume there will be no problems.
No, I don't think so.
Connect back again.
No, just reconnect back. It should work.
Okay.
The other panelists, you can stay here, or you can leave, and then maybe it's better that you stay here because I cannot say when exactly we will return. But in say, I guess, not less than in 15 minutes. Okay, see you then on the other platform.
Okay.
Okay.
So Anet, you're from Slovenia, or?
Yeah.
Okay.
You?
No, I'm living in Lausanne in Switzerland, but actually it's there are some people here who are Malaysians, and I think they could tell probably I'm Malaysian too, but I just haven't been. Yeah, I'm Malaysian too. So you see, David now is a.
Hello. Oh my gosh, so Jonathan, where are you now?
I'm in Switzerland.
Switzerland?
Are you based in?
The three of us are based in Malaysia.
Oh.
We're attending Harriet Ward University Malaysia campus.
Okay. Doing actuarial science or?
Actuarial science. That's how we started doing this. That's how we got into this competition, to be honest.
Yeah, okay, cool. Where is the campus in Malaysia? Is it in KL?
Putrajaya.
Okay.
When's the last time you came back?
I was just back 2 months ago, but I did the hotel quarantine. So I did hotel quarantine. But back then it was 7 days, so it was okay.
Okay. Does that mean you're vaccinated?
I am.
With how many doses, Anish?
2.
Oh, wow, great! Congratulations.
Either.
Yeah. Just one dose.
So that's the first dose, right?
No, but I will get the second one in 2 weeks. But Anish, did you get any side effects from your?
In the second one, I mean, okay, the shoulder hurts a little bit, but this is normal, yeah, I assume. But yeah, in the second one, I was just a little bit sick. So I got vaccinated in the morning, and when I went to sleep in the evening, I woke up, I don't know, at 1 a.m. because I was a little bit sick, yeah. But nothing special.
Yeah, I see.
Understandable side effects. Side effects are quite interesting though. I don't think it discriminates between young and not young. Because I'm doing an internship now, and my manager, actually my supervisor, had his shot last Friday, and the whole next day he was in bed, like feeling horrible. And then the next, on the other hand, my grandmother got both shots and had no side effects. So I think it doesn't really matter like how old you are. It's just genetics, I guess.
Yeah, but I don't know how it works, but I don't know. So once I heard that it's about how your immune system reacts. So if you have a good immune system, then you react, yeah, you are sick.
That's true.
But maybe for older people, I don't want to be rude to anyone, but no. Yeah. Because also my grandparents, yeah, they got vaccinated. It was nothing. So.
Okay. So side effects are good then?
Maybe, I don't know.
And you kind of know that the vaccines are working.
I don't know. But have you been vaccinated, David?
Sorry?
Have you been vaccinated?
Not yet. The rollout is a bit staggered in Malaysia. They started with the frontliners, then the older generation, and then now they're slowly moving to the younger crowd. So right now, I think it's mostly working adults.
Okay.
Yeah.
I see. And how is it in Slovenia? Like
it's really hot those days. Almost 35 degrees in Ljubljana.
Oh wow! Yeah. Do you live in Ljubljana?
Yeah, I'm not from Ljubljana, but I'm studying here, so I'm based here now. Yeah.
Actually, I haven't been to Slovenia, but I passed by Slovenia on the plane because I saw a lot of Slovenia from the plane because I had it was flying very low.
Yeah.
And I was flying into Croatia.
Yeah.
I had such a good view of the Alps and the Slovenian Alps, which is really cool. I forgot what the name of the tallest mountain is. It starts with T or something.
Triglav.
Yeah.
Yeah, you have some mountains, then a little bit sea, 20 kilometers of shore. Yeah. Yeah, in Triglav actually it means, I don't know why, because I was looking from all sides the mountain, but it means that it has 3 heads. So Triglav, it's like 3 heads. but I don't know where they were looking at it.
Let's see what Google has to say.
I think I can show you a picture of the picture I took of tree cloud from the plane, but maybe you can't see it so well. But I was very impressed that I could find it because I have a few Slovenian friends and they tell me about Slovenia, but I know it's a very small country, right? You are.
It's 2 million people, something like this, maybe a little bit more, but yeah. Yeah, it would be nice if we would have that meeting in Porto Rosso.
Yeah, well. So you didn't go as well, but you could have gone, right?
Yeah, but I don't know, but it's in Zoom anyway, so I don't know. I would go to Porto Rosso and then be on Zoom.
Yeah.
So I didn't find it reasonable.
Okay, I'm gonna take a quick break. I'll be back. See you guys.
So this is the picture. This is the picture I took, but you
Wait,
can't really see it. You can see like in the background. You can't really see it actually. I mean, but this is tree cloud. So maybe we can see the tree. Can we see a tree from the top? Maybe you can see maybe three. I don't know. Maybe I don't know. It's hard to see.
Yeah, a little bit. Cool. Thanks. All right. See y'all later.
Yeah.
And how did you find the challenge, Annette?
I mean, first I thought that it will be easy, you know, because it was set like, yeah, you have this, predict this, and then you just put everything into, I don't know, some algorithms. But then you know, you get.
Yeah, I understand. I completely understand. Also, what was crazy was that Rudy gave us the loss function like one day before.
Yeah, I mean, then I was actually not working anymore on so I just left the mean squared error and Poisson variance, because that weighted squared, that was, I don't know, you could predict negative. Then I saw that you mentioned in the comment, but yeah, you get.
Yeah, he didn't.
It's there, yeah.
Yeah, but he used another measure in the end. But the first loss function he gave, I was a bit confused as well. I was like, I'm not sure this is the right one. But
I think that Poisson, it's very similar to the weighted, because if you expand that logarithm to the if you expand it to the Taylor series, I think that the first term cancels out, or something like this, and then you just get the weighted, but weighted by the realized value, not predicted. So it's by the number of claims. So I think that those were similar, but.
Did you try like lasso? Like you could have, I don't know. It takes quite a while to run, but you could have done maybe like GLM with lasso. You know, like you could have done a Poisson GLM, and then with a lasso to choose which parameters to be bigger than 0, for example. I mean, I don't know if it will improve the prediction. I don't know if it will improve. Maybe not. I don't know. But
I think that there is quite a lot of things to try. But everything that you want to try, it takes when you start doing it, it takes a lot of time. And now we are actually having the exam period, so it was
Yeah. Good luck for the exam.
But I think that with the neural networks, I really think that would work good.
Yeah, I think if you, I mean, it just takes time to write your own loss function, right?
Yeah, but I mean, you can actually Google it when they are deriving the negative binomial, and then you have that loss based of maximum likelihood, and then you minimize that. Okay, yeah, you need to estimate those two parameters, I think, for negative binomial. But yeah, when we were trying in Python, okay, you have that 2D regressor that should work something like this, but I found it a little bit easier in R because it determines those parameters alone. I mean, you just optimize and then those parameters.
Yeah, I see. Did you use exposure as like, you normalize the GLM by exposure, but did you use exposure as a covariate also in the link function? You have to.
Yeah, I mean, I think that we did the same with the offset exposure.
Right, but no, I know you did the same with offset exposure, but I don't know if you did also. Did you also put exposure into the?
Actually, no, but I was trying. I mean, if you put exposure, it's useless because then you get exponential. I mean, you want to have linear dependence. So I think that the reasonable thing to do is to put log of exposure into that e to the power of log exposure, and then you get coefficient also in front of this maybe.
Yeah, so I mean, yeah, I was also thinking about that. I mean, that's related to the question I asked, because it seemed very crazy that in real life you would have also the exposure. I mean, it's like it feels like it's a bit of a cheat.
But I don't know what that exposure means. Is this the number of
no idea
persons insured? I mean, if it's just the number, then maybe you can. Okay, if you will have one group insured, maybe you can predict how big it is. Or maybe what I have also found out, sometimes exposure is the length of the duration when you have something insured, or maybe in years or I don't know.
Yeah.
Or I think that this was yesterday in one lecture here in the Congress. I think that also the distance was used as exposure. So if you need to drive more, you are more exposed now. So
I mean, it really depends, right? So the thing is, we know what exposure is, but we don't actually know what it is in this case anyway.
Yeah.
It was so funny with all these covariates. I was trying to guess like what F3 was or F13.
Yeah, I was guessing those. I thought that maybe those ordinal, where you have a lot of numbers. I was guessing that something is age of driver and the other one age of car. Yeah.
I was also guessing something like that. Yeah.
Then for one categorical, I was almost sure what it is. I think that it was like gasoline, or diesel or electric. Sorry?
F, I think. Petrol or diesel, and P, and I can't remember what it was.
Yeah, there were three categories, and one was named S D. The other one was I think B, benzene or something, and the third one E. So electricity, probably, because at electricity, we had very little observations also. So. But it didn't really help, I guess, because I don't know if you just want to know one.
I mean, of course, it doesn't help, but somehow it was funny to guess which was which.
Yeah.
I guess. In mind.
I think that there were also some on Kegel, if you take a look or something. They are already competing in things like this, and maybe you get the idea what might what those variables mean. Yeah, so there were density of population and something like this. But
yeah. Well, did you work alone or?
Actually, with Thomas, that is also here, and presented the third challenge. So at the beginning, yeah, we wanted to join, but so one of us preferred one challenge to the other one. Then we decided, yeah, we'll try to do like this. But then we were helping each other. So.
Oh, cool. Yeah. Well, it's I feel like these. That's why. I mean, that was the next question. Like, how did you choose which challenge to take? Because. Yeah.
Yeah. Actually, I mean, because of the study and exam period, the first one seemed the most time-consuming, but it was the most interesting, but the most time-consuming. That's why we didn't apply for that. But I think that would be interesting. Yeah. And yeah, okay, the fourth one. So this one, it seemed to be the easiest, but then once you start doing, you know, it's you are searching for improvements and everything, and it goes a lot of time. What about you?
Yeah, I read through the first three, and then the fourth one, I was like, okay, I'll choose this one. I mean, I didn't really have a plan. I also thought which one looks the easiest, but actually, if you look at the Slack, it seemed like our challenge was they had a lot of people in the Slack, right?
Yeah.
I don't know. I get the impression because I think it's the most like standard problem.
Yeah, I mean it's really standard if you have, but then there are those tricks, man.
Yeah.
And the second one, the theoretical one, I didn't even think about it because maybe after the summer break when you're free, you know, that you don't have so many equations in all the time. So yeah.
And the third one was, what was the third one? Yeah, it was the insurance. That one seemed quite popular as well.
Yeah, I mean, we were following it, but we were struggling a bit with the understanding of because maybe it was because you don't understand the problem exactly, and then
yeah,
it didn't really. I mean, you know, it looked like you have some steps that you need to follow, but on the other hand, it was try to do the best. That's it, and try to do something.
I just realized this conversation is recorded.
Yeah.
So good luck for your exams.
Yeah, thank you. And are you still studying?
Yeah, I'm still studying.
Which
I'm doing statistics.
Master, bachelor, PhD.
I'm starting my PhD, so.
Okay. Yeah, we are still in the master. We are now finishing the first year of master. So.
I'm very interested, so I think you might be suitable for a PhD. I think you like this kind of stuff, right?
Yeah, we were also working on one project with one insurance company last year, and I think that I mean it's interesting to me for such problems because you can really use the mathematics in in some useful way somehow. I don't know. Let's see.
Okay, so I think I'll take a break.
Yeah. See you maybe in 5-10 minutes. Yeah.
So welcome back. So the jury has finally reached the final decision on the winners. So as I already mentioned, we didn't get any solutions for the second assignment. So we had to decide who's going to be the winner for the first, third, and fourth challenge. And for the first challenge, the winner is Nguyen. Are you here?
Yes, I'm here. I'm so happy for that result. Thank you.
Congratulations.
Thank you so much.
And thank you for joining this competition. So for the third assignment, the the award goes to David and his team. So Nashi Limak or something like that is the name. So congratulations.
Thank you all very much. We had a lot of fun really doing this project and really learned a lot. Thank you guys for organizing this.
And for the fourth assignment, the prize goes to Jonathan Khan. So congratulations. Well, there we have decided that there will also be honorable mentions for the three teams which really do very well. So Thomas Roder, four mathematicians, and Danai Kovac. So your solutions were very much comparable to the ones that were awarded first prize. So with this honorable mention, you also get a financial reward in, so you get, each team gets 650 euros as an award. So the first prize is 1,250, and the honorable mentions will be awarded with 650 euros. So congratulations, and thank you all for joining this competition and using your time and skills to do it. Thank you. I would also like to thank the jury for the work the members of the jury have done. It was quite a lot of work, especially for some of the challenges. And I'm really grateful that they took the effort and helped us to successfully reach these final decisions. So thank you very much. Regarding the technical things about the words, I will give you the instructions